This is TPU. I know, unusual for this channel, but it has been a while. There's something special about this TPU though. Let's go. This video is sponsored by PCBWay. So this is Conductive TPU and it's made by Recreus. What we mean by Conductive TPU is electrically conductive. We'll figure out why in a minute, but the basic premise is that this is a flexible material that conducts somewhat electricity through it, both as a filament and as a printed part. The price of this stuff is about £50 a reel, which in dollars is about £50. This is, in my opinion, not terrible for a specialist filament of this kind, and that is for half a kilogram. I kind of get the feeling that you probably won't print large quantities of this, just down to the use case. Printing Conductive TPU is pretty straightforward. I've successfully printed it on every machine that I've tested it on, including the Prusa XL, which I'm using for this video for reasons that will become obvious later on. I've just used the standard TPU settings in the slicer. For Prusa Slicer that's flex setting, and I guess it can't hurt to slow it down a bit too, which is what I've done. That will make sure that you get a good solid extrusion, as that will presumably determine the conductivity. We'll see more about that later on. Recreus's Conductive TPU's shore hardness seems to be around, well, let's find out. Worth mentioning that officially the shore hardness of this filament is 92A, about the same and maybe slightly softer than most commercial TPUs. Either way, most modern printers should print this with zero problems at all using normal settings for TPU. There are some warnings though, so it's time to stir up the comments section by daring to look at the MSDS and pointing out things on the MSDS. It has the usual TPU-based stuff about cyanide. In case you didn't know, TPU is terrible if you heat it past a certain temperature. I always cringe when I see people talking about high temperatures with TPU. Don't do it. It's not a good idea to go over about 235 with TPU, just in case it overheats. I think it starts getting a bit dicey after about 250, but I'd have to look at the datasheet. There is some hint on this MSDS as to what's making this filament conductive in the first place, and well, they call it lamp black. Lamp black is also known as carbon black and a million other things. It's a pigment that is used in, among other things, paint and car tyres. It's just a type of carbon, and I'm not a chemist, but it looks moderately terrible to breathe as a dust, although I don't think you're likely to find that when printing, especially in small quantities. The dust is conductive, so it could ruin the electronics of the printer, but TPU doesn't seem to liberate much dust, if at all. I haven't seen any. So for a change, I'm actually of a view that this stuff is generally fine under the same precautions as you would use for normal printing of TPU, i.e. ventilate and don't breathe the smoke and don't overheat it. Obviously that's not official safety advice. For reference, I have a feeling it might be that a non-insignificant component of the dust that you get off belts of 3D printers may also be lamp black. Oh, and it's called lamp black because originally it was harvested from the soot inside oil lamps. So there you go. It looks like carbon black, lamp black, whatever you want to call it. It's also thermally conductive too, so that's interesting. So enough talk, let's do some experiments. Firstly, I want to see what the resistance of this stuff is, as Recreus are being a bit kind of secretive about it. They just say to contact them. The reason for this is because I think it's just depends. A basic test with a multimeter on a length of filament from the reel gives us these values on screen. This is about 1 kilo per centimeter, give or take, when held between two crocodile clips. Hilariously, or perhaps entirely expectedly, if you stretch it while it's held between those two croc clips, it will change resistance, because it's now longer. Testing again on a printed part oddly makes the resistance go up, so it conducts less. Although I think that's more about what I hinted at before with the it depends part. The resistance of a part is likely dependent on how much contact you make on the skin of the printed part with whatever you're connecting to it. And I think it's definitely how much pressure you apply at the same time. I imagine there's also a skin effect here too. In fact, I think I read that somewhere once. For reference, in case you're wondering, normal TPU does not conduct electricity at all. I did test it, I didn't expect it to, I just felt like I had to test it for some reason. So as part of this video, I collaborated with the sponsor PCBWay to make something that would allow me to run some further tests and do some cool stuff with this TPU. I realised a while ago that to show you some applications for this material, I would need to break out the Arduino, or in this case ESP32. What I wanted to make was a sort of prototype board with some ready-to-go onboard components like LEDs, switches, a screen, so I could just use it without having to wire spaghetti everywhere or having to solder or use a breadboard and loads of wires. This board is completely general purpose, so I'll be using it for a lot more things than just this video. I designed it in Fusion 360's inbuilt PCB designer, and the idea was to break out a large number of GPIOs on the ESP32. GPIOs are just ports to measure stuff or turn stuff on and off. If you don't know microcontrollers, it's basically just how you control things with a microcontroller through the GPIOs. But I also wanted to be able to access the ESP32 using wires instead of the connectors or the onboard components. So I have a bunch of screw terminals, and most of these are jumpered, so you can remove them and bypass the actual output and connect to a different output. You can do that because I've broken out the entire row of connectors on each side of the ESP32. It sounds very simple when you look at it, but I haven't seen anything else off the shelf that does this. I don't know why, or maybe there is and I just don't know about it. I ordered it as a PCB from PCBWay using their standard quick PCB service, and it was completely simple. You just upload the files out of the PCB software that you're using, in my case Fusion, and you mostly run with default options, maybe changing of colour or whatever you want. I went with green because it's quicker. You submit the order and they just make it for you. It was the first PCB I ever ordered from them. I've been sitting on it for a while waiting to make this video. You can even ask them to populate the board for you with components, but for this one most of the components were quite big and easy to solder on, and I had them here, so I did it myself. Having shown you that, I'm now going to use it, and I'm happy to say that it works 100%, which is not bad for the first try, even if I blow my own trumpet. What I've done here is programmed the screen to show the raw value from the analog to digital converter. The ESP32 has a lot of them. In simple terms, this is just showing you a proxy value for the voltage that the crocodile clip is seeing. Don't worry if you don't understand that. You can see that this value changes with distance. There's nothing entirely surprising there. It's basically the resistance goes up and down as you get closer to the other crocodile clip. The ADC on the ESP32 kind of bottoms out pretty close to the other clip because the resistance of this configuration is actually quite high. This is due to the high resistance of the filament. Interestingly, when I printed the same part but wider, it worked over a much larger distance. This is highly likely to be due to there being more material, which reduces the resistance. If you think about it, if I put several resistors in parallel in an electronic circuit, you divide the resistance down by the number of resistors you've got in parallel. Again, if you don't understand it, don't worry. Just the more area you have in width, the lower the resistance is kind of like a fundamental electronic principle. Now that in itself is quite interesting, but it means that you could potentially detect a squeezed part pretty easily by looking for a change in resistance. The simplest application for this filament is to design a switch, which actually turned out to be harder than I expected because of overhangs and things. I made it out of PLA and Conductive TPU on the Prusa XL, and it took a few iterations to make a print-in-place version that actually worked. Thinking about it, doing it on its side was the logical thing all the time, but for some reason I didn't think of that until much later on. Generally speaking, due to the resistances involved, you would still probably detect the switch being pressed by using the analog to digital converter on the chip, just like I was doing before, rather than looking for a circuit to go high or low, because it probably won't. Again, this is electronics, don't worry if you don't understand it. This is all good and well, but what I really wanted to do was make some annoying noises. Luckily, I'd foreseen this requirement by integrating a buzzer into the prototype board, a passive piezo, if you want to know, that you can program to make a tone easily. There's actually a tone command in Arduino, so it's quite easy to do. All I had to do was map that to the value coming in from the whatever I was touching with the crocodile clips, and fabulous. I feel like turning this into an actual thing that would be a video in itself, you know, actually making a musical instrument out of this, we'll see. It would be funny. We could talk about applications for this stuff as well. I mean, other than those we've already seen. The main challenge you have here with this TPU is the resistance, because compared to most conductors, the resistance is actually very high. This means that if you plan to run any kind of current through it, you'll probably struggle. If you want to light a string of LEDs, no, it won't work. It's therefore far more likely to be of use for more sensing applications, which is what I've been mostly showing you. One application I had planned for it, but not managed to get very far on, because it requires specialist circuitry it turns out, is to use it to sense strain, because as you can see, you can tell if it's being manipulated. Just fundamentally, it changes value for resistance when you squish it. This seems like a really cool application, 3D printed strain gauges. That could absolutely be a thing. I might try that in a future video. It is quite complicated. Otherwise, we're looking at switches, or maybe also water detectors, pressure detectors, capacitive touch sensors, things like that. There's a lot of options there. And all of this is printable, so you're able to make sensors that are entirely printed with no requirement to embed wires in them or anything like that. I think there's a lot of untapped potential there actually, and I think I've just scratched the surface. Let me know in the comments what you think about all this. If you have any other ideas on how to use Conductive TPU, put those in the comments as well. I will see you next time. Thank you for watching.